No. Just give it to us.
All right.
Yeah, give us a college algebra final.
Give you the college algebra final on Friday? You have 10 minutes to factor like Matt. All right, let's begin with prayer. Dear Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. All right. Any questions about anything before I get started here? Oh, I should mention Friday is when the bonus problem, if you're doing it, is due as well. So there's that. This is a kind of sort of hint for part of the bonus problem if you're doing it. If I was going to show an identity, I'd use calculus personally. All right. You could try to show this is true by squaring the Maclaurin series and adding them. You could do this. But I think that would be somewhat challenging. Unless you play games with complex arithmetic, in which case it'll be simple. But anyway, where was I? Oh, the juice. So I wanted to talk to you guys about conic sections. Unless there's, there still should be time for homework questions after this. So let's get through this, and then we'll do it. I am stealing from another professor today for what I'm showing you because what he has is nice. Let's see if I can find it. Whoa. Oh, yeah, go figure. When's the homework due? I have in the syllabus when that is. I don't think, well, I'm kind of torn. I don't really want to collect a bunch of this early. I want to let you guys have the time to work on it all the way. But I am kind of giving you the rope to hang yourself with because, there is what? 45 problems in this homework. So you should be working on it. I would strongly suggest you be working on it. If it'd be helpful to you, I can collect the first 20 problems on next Monday if you'd like. This is helpful. Some people are nodding. All right. Let me take a look at them and make sure that's a reasonable request, because I don't want to collect any of the polar problems yet, because we've not really talked about polar coordinates yet. About half of it's polar coordinate calculus, about the other half is parametric equation stuff. So the parametric equation stuff we've talked a lot about, but we still have more to talk about. Okay, so let me erase this. And so do you guys know what a conic section is? Why are they called conic sections? Yeah, if you take a cone and you slice it different ways, you get these different curves. So what kind of cone am I talking about? I'm talking about, sometimes we'd call a double cone. All right, it's actually like this. And so if you think about this, taking this three-dimensional shape, if you think about slicing it with different planes, that's what a section is, like cutting, right? And so if you just cut it horizontal, what do you get? You get a what? Circle from a horizontal cut, right? If you cut it like a little bit off level, you get one of these deals, right? Which is a what? Circle. This is an ellipse. What else can you get? If you cut the cone with a straight up vertical plane, what do you get? If you can imagine it, you could get these guys, right? You could get lines. A line is a conic section. There's also, if you just cut through the middle of it, a point is a conic section. Now, I think sometimes people would say a line and a point are degenerate conics. All right, so the genuine conic sections, if you will, are the circle, the ellipse, and there's two others. The other thing you could do And it starts to get harder to visualize, and that doesn't really matter too much, the visualization here. I just want to explain to you the terminology briefly. If you could imagine cutting this with a plane which just cuts through like the upper half, that's not it. How did it go? I guess the plane has to go like this, but you can also somehow get a, I can never draw that one, but there's also a parabola. I won't even try to draw it. There's a parabola. You can get a parabola. And of course the other thing that's easier to see is if you you do like kind of like a vertical thing but doesn't cut through the edge of it, you could end up with like a hyperbola. I can't draw that either, but you can also get a hyperbola in here. So these are the conic sections. Now every conic section can also be defined by some sort of geometric principle, all right? So let's work one out a little bit. And here's the first one. So geometric definition of conic sections. So the first one is a line. So if you take two focal points, say F1 here and F2, I'll put it over here, right? Two focal points, F1 and F2. If I take the collection, right? The collection of all points which are equal distance from these 2 points, what do you get? Well, first of all, you get the midpoint of these two guys, right? And then what else do you get? Point a little bit up here, a little bit down there, a little bit up here, a little bit down there, like this. Right, so you get this line. That is the collection of points which is equal distance from the two focal points, F1 and F2. Did you ever define a line like this before? Like, what? That's how you define a line? Well, that is one way you could define a line. It's the collection of points which are equal distance from two focal points. Now, the focal points have to be distinct, right? But if you do this, you can write an equation for it. If we say F1 is equal to, say, AB, and F2 is equal to, say, CD, then the equation we could write for a point, let's say R, which is xy. If we take a point on the line, what would the equation for it be? It would be the distance from R to F1 is equal to the distance from R to F2, right? Which is equivalent, you square both sides, right? Square both sides, what you got? You got x minus a squared plus y minus b squared is equal to x minus c squared plus y minus d squared. And this one's relatively easy for me to work out on the board, so I will do it. This gives me x squared minus 2xa plus a squared plus y squared minus 2yb plus b squared is equal to x squared minus 2xc plus c squared plus y squared minus 2yd plus d squared, like that. But something kind of beautiful happens here. I bought a lot of flooring this weekend, and the guy who sells the flooring at the Lumber Liquidators, he says everything's beautiful. We got tile in a basement. We got tile in the bathroom in the main level. He's like, beautiful. I'm like, I'm not sure it's beautiful, but okay. I see beauty in mathematics. So here we go. X squared and x squared, y squared and y squared. These guys are gone, right? And so if you look at this, you can collect terms, and what you got is you've got 2 times a minus c times x plus 2 times b minus d times y is equal to a squared plus b squared minus c squared minus d squared, which you could rewrite as something like this. Mx plus ny is equal to, I don't know, I need another letter. Chi. Oh no, that's a bad choice. Maybe what's that? W. All right, there you go. And so there you go. That's the equation of a line, right? This is the equation of an arbitrary line. Because you choose different choices for m and n, you can get vertical lines, you can get horizontal lines, you can get lines with non-zero slope. You got it all. Right? This is a general equation for a line. And I've just showed you how we can derive the formula which characterizes a line in terms of, this is what's called, this right here, I would put in the category of analytic geometry. Why is this analytic? Why is this an example of analytic geometry? Analytic, I can't spell. Analytic, geometric. Because what? You can see it in terms of the constant. I'm just saying something more, less I mean, all I'm really saying is you have a formula for it, which means you can analyze it. What I started with, some people might also say what I started with was also analytic geometry. Right? But that I would say is sort of more vector theoretic, right? What I started with, I would say, is more close to just pure geometry. You know, what I had at the start, the sentence that it's the collection of points which are equidistant from two focal points. That's definitely formal geometric, right? That's what Euclid did 2,000 years ago, and it doesn't get very far, because without equations, it's really hard to solve problems. With equations, all of a sudden, though, if I ask you where does this line intersect another line, say x equals to 2, you know what to do. You plug 2 in and you find y. That tells you where it intersects. Piece of cake, right? So once you have a formula, you can do so much. You can do so much analysis. And of course, we know how to do calculus with a formula, right? How do you do calculus with this? I don't know. So let me just rattle off the other definitions for you, and then I'll show you this PowerPoint. So a line is the collection of all points equidistant from two focal points. What's the next thing you can do? You can talk about the collection of points which are equal distance from, say, a focal point and a line, right? What is the collection of points that are equal distance from a focal point and a line? The line's called the directrix. What's that? Parabola, right? So the parabola looks something like this, right? Parabola. How do you define an ellipse? What's an ellipse? It's the collection of all points which are, and this is a little bit more complicated, where the sum of the distances between two given focal points is held constant for all points on the ellipse, right? This is an ellipsis. It's a collection of points such that the sum of the distances for two given focal points is held constant. What's a hyperbola? It's the collection of all points such that the difference of the distances from two focal points is held constant. All right. So I have some visualizations of that to show you. And this is from Dr. Sprano. He made this pretty nice PowerPoint for this thing. I'll show you. Well, I'd like to show you. Come on. All right, let's try this again here. Well, thank you. If I can find my laser. So, as I said, Dr. Sprano gave me the, so here's the parabola. Parabola is like I was just telling you. All right. Here's the focus. Here's the directrix. And he does these little animations. So as you can see, the length of this line and the length of that line are equal, which makes that point a point on the parabola. All right. Let's do the next one. Did it do anything? No. Here we go. All right. Yeah. There's that one. So there's another point. I'm going to speed this up a bit. You guys didn't know Dr. Sprano was such a silly person, did you? Let's see here. So, there you go. Okay, so as you can see, these these points here, right? They're equal distance from the focal point and the directrix, each one, if this was done exactly correctly. And I wouldn't go measuring things on this slide if I were you. But the spirit of the thing is right? So here's another picture of the parabola. And he points out that the equation of it is ax squared with a greater than 0. So what he's trying to do is now relate the standard formula for the parabola to the formulas for the directrix, okay? So here's how it goes. The focal point is 0p, and the directrix is at minus p. All right. So he's situating the parabola in that way. I mean, you could put a parabola any different which way, and it would have different equations, right? And so there's your directrix and your focus. The axis of symmetry goes through the. Woo! All right. Great. Let's get to it here. So if we take any point on the parabola, what can we say? X comma minus p is the point on the directrix where the perpendicular intersects. All right. So that's down there. And what's the distance? So it's easy enough to, what's this distance here? Yeah, y minus, so I think y plus p, because we're taking p to be positive. So, I mean, in terms of a formula, it's this distance, which is y, and that distance, which is p, so it's y plus p. And then whatever this is, which would be what? The square root of x squared plus y minus p squared, right? Distance formula. So there you go. And so if they're equal, you get this equation down here, right? Which then you can square and solve, and you get x squared is equal to 4yp, which gives you this formula, 1 over 4p equals this. So if we have a parabola through the origin, and you want to know where the focal point is, it's apparently equal to, the coefficient of it is 1/4 over where the focal point is. So for example, for the standard y equals x squared parabola, the focal point is where it's at 0, 1/4. All right. If you were making, like a parabolic reflecting mirror, this might be important to you, right? So, the ellipse. Now here is where Dr. Sprano's PowerPoint slide really shines. Check this out. So here's your focal points, all right? And he takes this, you could think of this as a piece of spaghetti, I think is what he says. So you take a bunch of spaghetti sticks, right? And you break them. And when you break a spaghetti stick, how long is it? Well, it's not how long it is, right? And so if you put those together, that gives you a point on the ellipse. Break another stick, get another point. Break another stick, get another point, and another point, and another one, and another, and another, and another. There you go. So this kind of shows you a craft you can do with little kids if you want to illustrate an ellipse with doing what? You get a box of spaghetti, and you have them break them into different, size lengths. Pick your 2 focal points, and then you can glue them on the paper and then trace out the ends which are reached. You should get an ellipse. Or you could just take 2 thumbtacks and put it into a cork board and take a piece of string, a loop of fixed length, and then go around, right? Because if you do that, if you have a loop of string between 2 focal points like this, right? And you hold the string taut, what's the deal? Then this length here is always held constant, right? So it's always the case that this distance and that distance are equal, right? Well, not that they're equal, but d1 plus d2 is equal to constant. So if you kind of, well, I can't do it justice, but anyway, you get the idea. So sometimes I try to get like a suction cup and put it on the board and have a big piece of string and like trace out the ellipse, And then the suction cup always comes undone, so I'm grateful for this PowerPoint. You can figure out, if you look at this is the semi-major axis, it's, well, that's a special one in terms of how it relates to the distance which is being held constant. Now, the nicest equations for an ellipse you get, okay, so like, you could think about putting an ellipse anywhere, right? And the equation for an ellipse anywhere, they're complicated. It could be rotated. all right? And it wouldn't even look like the formulas I'm going to give you. But this one, if the focal points are chosen to be nicely symmetrically situated with respect to the y-axis, that's when we get the nicest formulas. So we're going to derive the formula in the nicest case possible, all right? And if you do this, we will call the coordinates of the focal points C0 and minus C0, like that. If xy is any point on the ellipse, what do we have? We have the sum of the distance from the one focal point to the other is held to a constant, which Dr. Sperano calls d. Now, when I've done this derivation in class, I figured out what d is. You could figure out what d is from the outset, because if you look at it, if you look at this furthest point here, which we would call, we give it any name we want, the standard name for it is a comma 0. And can you tell me how a comma 0 right here would be related to d? Well, think about it. It's this distance plus that distance. What's this distance here? This would be a minus c, right? If this is a0, this would be a minus c. What would this distance over here be? It would be a, which is here, right? Plus this distance, which would be c. So you have a minus c plus a minus c. I could say it. Anyway, the c's cancel. You just get 2a for this point. In terms of the distance, the d would be 2a here. All right, and d is held constant. So this d can actually be shown to be twice whatever the coordinate is there for x. All right, but Dr. Sperano doesn't put that in at the start. He just works with d, which is fine. You can do that. You know, it's all good. And so you want a nice equation, right? Have I ever told you guys this is the equation for an ellipse? I have not, right? What do we always do? We always reference those super nice formulas, which I have a printout for you guys. So take a couple of passes, well, just one here. I'll start at a couple different places. But on this sheet, I've got all the standard formulas for you. And so my point to you would be that we do not have, I see 1, 2, 5, 8, 13, 18, 20, 24, 26. We should be fine. I got 30 of them. There's only 28 people in here. Okay, so my point to you is this is not the equation that we use for an ellipse, right? What's our equation? Well, when this finally gets passed around, I should have 2 left. Who's missing one? Who's still missing? Did I miscount? Everybody got one? So if you look on here, you know, the equation for the ellipse, well, I've got an equation for a short ellipse and I got an equation for a tall ellipse. But as you can see, either way you slice it, you can make it x squared over a squared plus y squared over b squared equals to 1. All right? Although I changed the meaning of a and b. The reason, like usually I don't care about which is a and which is b in this sense because I don't usually care about where the focal points are for the ellipse. But if you care about where the focal points are, you have to sort through these issues. All right, so that's why there's a distinction between which is a and which is b on this formula sheet. So we spend a great part of our existence in calculus without caring about where the focal point is for the ellipse, right? I mean, I've not cared about it for years. It didn't hurt me. But that's mostly because, well, there's no good reason for it. So if you solve this, you got to get rid of the square roots, right? So you isolate one square root, square that thing, you get that, all right? And then what? Isolate the root again, square it, right? Then multiply it out, collect like terms, do a little bit more rearrangement, a little bit more rearrangement, a little bit more rearrangement. Now it's starting to look like our standard equation, right? So now he finally introduces a and b as the coordinates of this point and that point. Well, next slide. Here we go. There they are. And so with that in mind, he points out that, well, if you put y equal to 0, you get d squared is equal to 4a squared. See, I argued that d was equal to 2a geometrically, right? I gave you a geometric argument. I was pointing at the different distances and adding them, yeah? What's Dr. Sprano done? He found the equation, then what did he do? He just plugged y in. It's just pure algebra, right? Pure algebra. No geometry in sight. You can simplify this derivation a little bit if you use some geometry. But anyway, so the total distance is the length of the major axis, right? So the length of the major axis, it goes from here all the way over to there. That's 2a, right? And this, it turns out, is the length of the semi-minor axis, which is 2b, which he'll derive next here. And so the relation between the focal point where it is c and the a and the b is that c squared is a squared minus b squared. So there you go. This is the equation for a horizontal ellipse centered at the origin, x squared over a squared plus y squared over b squared equals to 1, where what's the conditions? The length of the major axis is 2a, the length of the minor axis is 2b. The focal points are where c squared is equal to a squared minus b squared. For this to make sense, of course, we do need that a is greater than b, right? What happens when a is equal to b? The focal points are the same point, and this ellipse becomes a circle. And the semi-major and the semi-minor axis both have the diameter, which is 2a, or 2b, however you want to look at it. Now the hyperbola, he actually has a, here's his, so check this out. This is kind of sneaky. So what he does is, if you want the distance to be fixed, he says, you want the difference between the longer line and the shorter line. So if you take the longer line length and subtract the shorter line, it should be held fixed at this distance, whatever that is. That's what a hyperbola is, right? And so puts them up there like that. And then there's another one. I'm not sure what you could, I mean, you can't do this with spaghetti, can you? Maybe you can if you have like you need like a reference thing to break it with. I don't know. It's a mess. I don't have a good way to make a child's craft for this one. But here it is. There's the points. That's roughly speaking a hyperbola. And you can do the same thing on the other side, and you get the other branch. There are your focal points. And then guess what? We have this equation. How do you find the nice equation for it? You take this geometric definition, and you isolate the radical. You square it. Right? I think it's a good exercise for any math major to actually work through these. If you haven't worked through these before, it's like a trial by fire. Like, you can do it, but it is tedious, and it will take you some time to get it right. So like it's basically the same thing. Isolate the radical, square it, and then isolate the radical again, square it, distribute the terms, collect like terms, cancel like terms that you can, and you get yourself to this, which then, you know, he points out the difference between that and the ellipse. And lo and behold, we have x squared over a squared minus y squared over b squared, where the relation between the focal points and the a and the b constants is this time c squared is equal to a squared plus b squared. Isn't that kind of funny? So for the hyperbola, the relation between the constants is kind of the Pythagorean identity, right? But for the ellipse, we had the c squared was a squared. What was it? I've already forgotten. Gah! That's why I need this. That's why I need this sheet. Or was it? What did you say?
C squared is a squared.
Yeah, c squared is a squared minus b squared for the short ellipse, as I call it. In fact, I have arranged so like if you look at the sheet, all right, the game I'm playing is I'm making the thing. I'm basically moving the a and the b label to be the dividing by the Cartesian variable to make the formula for the focal point the same. You understand, if you were a book which made a always go under x and b always go under y, you'd have a different formula for the focal point for a short ellipse versus a tall ellipse. This handout makes the choice to make the formula always the same, but the defining equation for the ellipse different in the case of the short versus the tall ellipse. Beware of this issue if you're trying to do something kind of detailed analytics with this, because if you're not, it will throw you for a loop. But anyway, there's the equations for the hyperbola, and yeah. So I thought I should show you that because I doubt you guys have seen it worked out in detail. How many people, show of hands, who has seen the conic sections derived in your algebra class? I see 1, 2. Nope. I mean, I didn't. So, of course, I did have college algebra from a lady who was, she was tired. She taught in the high schools for 20 years, and I got to the start of the class was, I've chased students in the hallways for 20 years. I'm not chasing you guys. If you don't want to come to class, don't come to class. I don't care. If you want to don't do your homework, I don't care. Don't do your homework. She would put up to 90% of the grade on your final. So like, she was fun. I can't remember her name, but she was fun. I used to ask her questions like, could you do such and so forth? And she'd be like, well, James, you can do it that way if you want, but the rest of us are going to do it this way. I heard that more than once. I'd be like, all right, I guess that means I'm not wrong. Probably. I had recently discovered this program called Derive at the time. Derive is a DOS-based precursor to Wolfram Alpha. Derive is what it sounds like. It would derive algebra. And this is like a, text-based prompt, it's like it's way before Mathematica, right? But it could do things like factor complicated polynomials and stuff like that, so it was fun. Here you go. Here's a list of problems we could try. So we could either work on this problem sheet here, or if you guys have questions about your homework, we could do that. Next class, I'm planning to start polar coordinates, all right? Friday, we'll have a quiz. Oh, you already got it. Okay. Friday, we'll have a quiz on parametric equations. I do have an example in mind that I probably should show you. Everybody got one? Anybody missing? So these are just some good examples. Let me do one kind of like your homework that is not on this sheet actually. If I can get this out of the way. Oh man, what did I not do? Oh man, this is so embarrassing. What have I not done yet? Oh yes, that's right. How dare I not give top hat the time of day in here? What is wrong with me?
Good question.
Well, many things, yes. I should not ask that. Let's see here. Oh, that reminds me, I need to make an announcement in physics. I will make the following announcement in physics. This is the time of year upon which we are in the season of engineering end-of-term projects. As such, if you have such a project to do, don't do it in my class. Do it somewhere else. Do not bring your laptop to class and work on other things in my class, because eventually it makes me angry. So something like that I need to announce. Let's see here. Where was I? You guys wouldn't dream of working on your laptop in here, right? Because this room is small enough that you realize this is a classroom and you should pay attention. The physics classroom, on the other hand, is 4 times the size of this room and communicates exactly the opposite message. Like, paying attention is optional. So anyway. So here's the one I want to talk to you guys. So suppose and I'll make this problem worse. I'm going to make this worse than your homework. Suppose you've got PQR, and I'll pick a fourth point S. Suppose you wanted to find a parameterization that goes from P to Q to R to S. All right? And I'm not even going to give you coordinates for these because I want to encourage you to think about it sort of more vector geometrically. All right? So we want to find a parameterization of this line segment. And I want to make this for, 0 less than or equal to t less than or equal to 1. In other words, I want this point P to correspond to t equals to 0, my parameterization, and I want s equals to be my t equals to 1, my endpoint. All right, I want to find a parameterization of this piecewise defined curve, which I think is what Sam was starting to ask me about last time, and I didn't quite, I forgot I asked that homework question. So, so I just wanted to share with you a simple idea, which is this. First of all, before I do all this, something I should mention is if you just have 2 points, P and Q, there's an easy go-to formula for this. You want to parameterize this, t equals to 0. You want to parameterize that, t equals to 1. What's the vector parameterization of it? Well, just r of t is equal, oh man, this marker really, really stinks. P plus t times q. I mean, this marker smells like death. Ah. Oh man, it's bad. What do they do? What animal did they kill to make this? I don't know. Anyway, so check this formula out. What happens when you put r of 0? See this? This is gone. You get p, right? Put r of 1. You get p plus q minus p, also known as q. So this is my go-to easy way to parameterize a line segment. You need to know this. This is like an important trick. It'll save you tons of time, right? If you want to find the parametric equations for that, we need to know the coordinates of the points, right? For example, if I had p is equal to 2, 3, and if I had q is equal to minus 1, 7, then we get r of t is equal to 2, 3 plus t times, let's see here, minus 3, 4, which of course is 2 minus 3t, 3 plus 4t, all right? And so sometimes I've made it, there's some homework problems where I've asked you, I asked you for the vector parameterization of the curve, and I also asked you for the parametric equations for the curve. So for this here, what would the parametric equations for this curve be? You just have x equals to 2 minus 3t, and y is equal to 3 plus 4t. Okay, so these are the so-called parametric equations for the curve, whereas this is the vector parameterization of the curve. Or you could call this this is a quote-unquote vector valued function of time. The input is time, the output is a vector, one for each time, all right? Okay, so with that backdrop, this more complicated problem, we want to use that, but it doesn't quite work, does it? Because, any ideas? What could I do? So I want the whole time to go from p to q to r to s to be 1, right? So if I make it a uniform, if I make it a uniform time, I would make this what? Time what? And make this what? Time what? 1/3, 2/3. Yeah, 1/3 and 2/3. I like that. What's that? Assuming it's the same distance. Yeah, I mean, assuming it takes the same time. They don't have to be the same distance.
It would speed up.
Yeah, right. Oh yes, that's right. It would speed up. So the formula to get that is just this, r of t, and you do case-wise, all right? So like the first case is just p plus, 3t times q minus p. 0 less than or equal to t less than or equal to 1/3, right? Try that out. See, when you plug in 0, you get p. When you plug in 1/3, you get 3 times 1/3, which is 1. It's basically just running my standard trick 3 times as fast. And we'll do that for each leg. The next leg, we'll do q plus 3 times t minus 1/3. times, let's see here, r minus q. 1/3 less than or equal to t less than or equal to 2/3. That's a nice way to do this, because you see what happens when you put in a third, you get q, so it matches up with the last leg. It continuously joins it, right? But when you plug in 2/3, what happens? When you plug in 2/3, you get 2/3 minus 1/3, which is 1/3. 1/3 times 3 gives you 1, so you get q plus r minus q, otherwise known as r. R. And did I ever tell you guys about the pirate captain? I don't know if I ever told you guys about the pirate captain. When I went to NC State, I may have told you this before, I don't know if I did or not, but when I went to NC State, or maybe when I was in grad school, I can't remember which, there was a guy who ran for student government. He called himself the pirate captain. They didn't have in their bylaws that you had to run under your real name. So he ran under the fictitious name, the pirate captain. And he won. Oh, he won by a lot, because it turns out most people don't respect student government, go figure. And he went to all of the meetings dressed as a pirate, and he would only answer in pirate lingo the whole year. His platform was actually the mocking of student government, and it was a resounding success. So if he could have abolished student fees, it would have been, I mean, he would have had my ultimate respect. Anyway, S minus R. Yeah, I mean, tuition's freezed, but our student fees? I'm guessing not. Am I wrong? Have student fees gone up since you've been here? So has housing. Okay. They what?
They locked the tuition.
They locked the tuition, but they did not lock the fees, did they? Right. So, gotta shut down all those club sports. I'm sorry. Is that what fees pay for? I don't know. Something pays for club sports.
$700 activity fee.
A $700 activity fee? Oof. I guess you better go use that Snowflex. Make it worth your while. But what's that? Snowflex is not free? Oh. Well, at least that'll keep you from getting hurt. All right, so it was funny. When that first opened, like, the athletes were forbidden from going on it because they kept getting hurt the first couple of weeks. Anyway, so there you go. So if you understand this more complicated example, the homework problem with 3 points should be easy enough to see, right? You just, instead of doing a third, do a half. And you can see that you could, basically generalize this if you have any piecewise collection of points, if you want to. But you're right, they have different speeds. See, because the velocity vector is essentially equal to, in this one, the velocity vector is q minus p. In this one, the velocity vector is actually r minus q. In this one, the velocity vector is actually s minus r. If you differentiate these with respect to time t, you just get these displacement vectors. And those don't have to be equal length. So you're right, they would have different speeds corresponding to the different points. Yeah.
How could you standardize speed and distance?
Oh, yeah. So if you wanted to make constant speed, I would need to find the total distance. All right. And if I wanted to still make it, times 1 unit at a time over the whole journey, then I would have to proportionally, take enough for each. If the arc length was 10, and between p and q I had 1 unit of distance, I would want t to range from 0 to a tenth. And if the distance from q to r was 7, I would want.
So the distance ratio instead of.
Yeah, something like that. Yep.
We're not allowed to use this for just general, ellipses and circles and stuff like that.
So for ellipses and circles and stuff like that, you want to use the sine, cosine, or cosh sinh. So if you look at the sheet, right? Oh man.
Plus or minus answers that you have to piecewise.
Let's see here. So notice that the third thing down on the sheet, I have the ellipse centered at HK. So the derivation I showed you today from Dr. Sprano was for an ellipse centered at the origin, right? Well, what happens if the ellipse is not centered at the origin? Well, it has different equations, right? Like x minus h squared over a squared plus y minus k squared over b squared. And in the curly brackets, I give you a nice formula to parameterize it if you want it to go counterclockwise. And then you just have to limit the domain to select the part of the ellipse that you're interested in. for a hyperbola on the other side, I should have, oh, come on. Do I not have it? Son of a gun. Yar. One moment. Give me a second here. I will find it. So the thing I'm about to post for you guys, there's some duplication. So like the PDF I have already currently posted has a lot of things for you about parametrized paths, right? So if you look in there, I think I have the formulas. Maybe I'm wrong. Well, I give you examples, right? Maybe I should look at the other one. So here's what I'm planning to post for you guys, hopefully today. I'm going to stop letting perfect be the enemy of good. So like the last section is currently unfinished, and that's okay. That's okay. The other problem with this is my polar coordinate stuff is first, and then I have the, oh, come on. Oh, man. Oh, here it is. So section 4 point, well, really? So in this thing I'm about to post, I have the formulas for it. Parameterization of hyperbola in section 4.7 here. So if you're dealing with this kind of hyperbola, you can use cosh for this piece and sinh for that piece like this. And then that will get the right branch of it, right? If you want to get the other one, you use minus for the cosh, something like that. And here are some other formulas for parametrizing hyperbolas. But basically use cosh and sinh and think through it is, in a nutshell, it. One last thing just to finish today. I've only been talking about conic sections which are done, which are what? Something like right. And so if you let these go around different values, what's going to happen? You get either, nothing, or you get a hyperbola, or you get an ellipse, right? But what's interesting is if you add another term, all right, a couple more terms here, like then let me stop that. What happens, go away, is as you can see, you get, what are these? They're sideways, right? So if you include a mixed term like 2xy, what that does is it rotates the conic section, and so it's no longer symmetric around the xy axes. So to discuss those properly, you have to introduce rotated coordinates, which we don't traditionally do in calculus 2. All right? And so I can tell you how to find those in linear algebra. If I taught 221, we'd go into that in depth. But anyway, I haven't, so hey, happy convo to you. If there's a convo today, is there a convo today? Yes. All right, well, happy convo to you then. Watch out for the false teaching, of course. But anyway, yes.
Yeah.
Always.